First, for introduction, population dynamics is the study of changes in population size and structure over time, influenced by factors such as birth rates, death rates, and migration. Understanding these changes is essential for resource planning, ecosystem management, and policy making. One important tool for modeling population dynamics is Leslie matrix, a mathematical model that organizes the population into age classes and uses fertility rates and survival probabilities to predict future population changes. The Leslie matrix is widely used to analyze population growth or decline and study the effects of changes in fertility and mortality, and determine long-term growth rates and stable age distributions. In this project, we focus on applying the Leslie method to a chosen population, leveraging eigenvalues and eigenvectors to gain insights into its long-term dynamics.
For the methodology, step 1, describe the issue by determining the survival probability, fertility rates, and population classification. Then step 2, construct the Leslie matrix. And step 3, represent the population by define the starting population vector P sub 0. And step 4, iterate population dynamics to determine the distribution of the population in the future using the formula below. For the next step, we execute eigenvalue analysis to determine the dominant eigenvalue by calculating the eigenvalues and eigenvectors of L. Then step 6, we analyze the finding, and also last step, verify and project to ensure alignment with eigenvalue-based prediction, project the population over a number of time steps. Let's look at the example. Given fertility rate for adults, which is 1.2, and also survival probability for juveniles, which is 80% of juveniles survive to become adults, and 60% of adults survive to the next year. And the initial population is 100 juveniles, which is age 1, and 50 adults in age 2. Then we construct the Leslie matrix by creating a matrix L with fertility rates in the first row and the survival probabilities in the subdiagonal. Then we represent the population by define the initial population in the vector P0. Then we calculate the population in the next year using the formula P1 is equal to L multiply P0. Then we solve for eigenvalues and eigenvectors of L, and we identify the dominant eigenvalue. Then we can interpret the result using the dominant eigenvalue for the long-term growth or decline trends for the corresponding eigenvector for stable age distribution. And also we verify and the project to confirm alignment with the eigenvalue-based predictions.
Result and discussion. So, to analyze population dynamics, we use a Leslie matrix which models age structure codes. Here we consider a population divided into 3 age groups. Like age group 1, we have 0 to 15 years. In group 2, we have 16 to 13 years. And group 3, we have 31 to 45 years. We also have fertility rates and survival probabilities. And then we put it into the Leslie matrix and assume what is the initial population projected population vector, which is for the group 1 we have 1000, group 2 we have 800, and group 3 we have 600. So and then we calculate the P1, which is the population projection like in the calculation above, and then we calculate the eigenvalues and eigenvectors. So first, to calculate the eigenvalue and eigenvectors, we need to find the eigenvalues used, determine determinant where I is an identity matrix, and then we get the answer, and then we do the determinant by each subdeterminant, and then we will get the answer. So like the calculation above, we get the characteristics equation is like lambda 3 minus 0.69 lambda and minus 0.24 equal to 0. So after that, we approximate the eigenvalues. For the dominant eigenvalue, lambda 1, we get like 1.2, and then for lambda 2, we get negative 0.3, and lambda 3, we get negative 0.6. So for lambda 1 as a dominant eigenvalue, we represent it as a population growth rate, and for lambda 2 and lambda 3, we represents it like related to transition dynamics. And then after we settle with eigenvalue, we need to calculate the eigenvectors. So after we calculate the eigenvectors, and then we will get the answer like lambda is eigenvector that corresponding to lambda equal to 1.2 is V, 1.5, 1, and 0.5. So we will get the answer like 50% of age population is in age group 1, 33.3% is from age group 2, and 16.7% of age group 3, like as the answer that given in the result bar. So for the discussion, we know the numerical methods of eigenvalues dominance indicates a 20% population growth per step. So the corresponding eigenvector normalized to sum. So 1 represent the stable age distribution, like this eigenvector shows the proportion of individuals in each group as the population stabilizes. So the dominant eigenvalue indicates a growing population with a long-term stable age distribution of 50% in age group 1, 33.3% in age group 2, and 16.7% in age group 3. Fertility rates and survival probabilities significantly affect these outcomes, and adjusting these parameters that can help manage the population growth and structure efficiently.
As a conclusion, the Leslie matrix model provides important insights into population dynamics by utilizing eigenvalue analysis to ascertain stable age distributions and long-term population growth rates. Through the analysis of fertility rates and survival probabilities, the model assists in identifying critical age groups, allowing for focused interventions to successfully sustain or recover population. The model also offers useful solutions for population planning, sustainable resource use, and biodiversity preservation, and is widely used in a variety of fields, including ecology, fisheries, forestry, and human demographics.